Welcome to the Basic Electronics series. Today we will be learning about operational amplifiers and oscillator circuits. Here is the agenda: operational amplifiers, introduction, symbol, parameters, configurations and circuits. Then oscillator introduction, condition for oscillations, ladder network oscillator, Wein bridge oscillator, single stage astable oscillator and crystal controlled oscillator. So this is the introduction. So operation amplifier, which is also called as op-amp. So it is a very high gain differential amplifier with high input impedance and low output impedance. It offers all advantages of monolithic integrated circuit like small size, high reliability, reduced cost and less power consumption, and these are used in applications such as adder, subtractor, multiplier, integrator, differentiator, rectifier, comparator and instrumentation amplifiers, etc. So this is the symbol. Here you can see the device features two inputs. One is an inverting input and one more is non-inverting input. The inverting input is denoted by minus sign while the non-inverting input denoted by plus sign. The plus sign represents 0 phase shift whereas minus sign represents 180 degree phase shift. And next is the operational amplifier parameters. First is the open loop gain. So it is also called as open loop voltage gain. It can be defined as the ratio of output voltage to the input voltage measured with no feedback applied. So here feedback is not there. It may be thought as the internal voltage gain of the device, and this is the equation V out divided by V in. So this value is exceptionally high, means it is greater than 1 lakh. The open loop voltage gain is often expressed in decibels also. That time we can write formula as 20 log 10 of V out divided by V in. So most operational amplifiers have open loop voltage gains of 90 decibels or more. And next is the closed loop gain. So it is defined as the ratio of output voltage to input voltage measured with a small proportion of the output fed back to the input. That means here we have feedback, here no feedback. The effect of applying negative feedback is to reduce the loop voltage gain, and this is the formula V out divided by V in. So the value of AV means closed loop. In closed loop, the voltage loop gain value is very much less than the value of open loop gain. And next is the input resistance. It can be represented using R in. The input resistance of an operational amplifier is defined as the ratio of input voltage to the input current expressed in ohms. The ideal value is infinity and practical value ranges from 2 mega ohm to 1012 ohm, and it is given by the formula R in equals to V in divided by I in. Next is the output resistance. So it is defined as the ratio of open circuit output voltage to short circuit output current. It is expressed using the unit ohms. The ideal value is 0 ohm and practical values ranges from less than 10 ohm to around 100 ohm, and it is given by the formula V out divided by I out. Next is the input offset voltage. So an ideal operational amplifier would provide 0 output voltage when 0 difference is applied to its input. So in practice we can say that due to imperfect internal balance there may be some small voltage present at the output. The voltage that must be applied differentially to the operational amplifier input in order to make the output voltage exactly 0. So that is known as the input offset voltage. So it may be minimized by applying large amount of negative feedback. So ideal value is 0 volt and typically values ranges from 1 millivolt to 15 millivolt. And next is the full power bandwidth. The full power bandwidth is defined is nothing but it is equivalent to the frequency which is the maximum undistorted peak output voltage. Swing falls to 0.707 of its low frequency value. So full power bandwidth ranges from 10 kHz to over 1 MHz. And next is the slew rate. So it is the rate of change of output voltage with time. Here you can see delta V out divided by delta T. So when a rectangular step input voltage is applied, so this will happen. So it is the rate of change of output voltage with time in response to a perfect step function input. So delta V out means it is the change in output voltage and delta T means corresponding interval of time. So this is about the operational amplifier parameters. And next is the operational amplifier configuration. So inverting operational amplifier. So input signal V is applied to the inverting terminal of the amplifier and output is V out is inverted version. So here 180 degree phase shift. So of input V in. So here you can see we have given input like this and we got output like this. 180 degree phase shift happened here. So input V in applied to this inverting terminal. So this is the input inverting terminal, that is indicates using the minus sign. So here 180 degree phase shift happened means it is inverting the input. The gain expression is given by V out by Vi is equals to minus Rf divided by Ri. And next is the non-inverting operational amplifier. So input signal Vin is applied to non-inverting terminal means here we applied this is to plus and output is V out, that is non-inverted version means 0 degree phase shift of input V in. So here you can see what input you have given, the same output you got. There is no phase shift happen. So the gain expression is given by V out divided by Vi equals to 1 plus Rf by R1. And next is the differential amplifiers. So differential amplifiers amplify the difference between two input voltage signal, that is V1 and V2. So here you can see two input we having, one is V1 and V2. So V out means difference between two input signal V2 minus V1. So that is about the differential amplifier. And next is the operational amplifier circuit. The first is the voltage followers. So this amplifier has a voltage gain of 1 and very high input impedance and very high output impedance. So this is also referred as a buffer, means whatever input you given, the same output you got here. And it is used for matching high impedance circuit to low impedance circuit. So output voltage V out follows the input voltage V in. So the circuit is named as a op-amp voltage follower. The output is connected directly back to the inverting input. So this is minus, right? So that the feedback is 100% and Vin is exactly equals to the Vout. This is the voltage follower. And next is differential amplifier. So differentiator produces an output voltage Vout that is proportional to the rate of change of input voltage Vin. Here you given a square wave and you got output as a pulses. So, and this circuit uses capacitor C in series with the input voltage Vin and a feedback resistor R is connected between Vout and the Vin to the inverting terminal. So this is the differentiator amplifier. And integrator amplifier, so here it produces the output voltage Vout that is proportional to the integral of the input voltage Vin. So an op-amp is an inverted amplifier. So it has resistor R in series with input voltage and capacitor C connected between Vout and Vin to the inverting input. So this is connected as a feedback. So if input is square wave, you will get a triangular wave, that is inverted wave. And next is the comparator. So a voltage comparator compares the magnitudes of the two voltage inputs and determines which is the larger of the two. So the output voltage produced by the operational amplifier will rise to the maximum possible value. So whenever the voltage present at the non-inverting input exceeds that the present at the inverting input. So here you can see the comparator. So what comparator will do means it compares the two signals V1 and V2 we having. So and which one is bigger by giving an on and off output. So that will compare. So that means it compares the magnitudes of two voltage inputs and determine which is the bigger of the two. The output voltage produced by the operational amplifier will rise to the maximum possible value whenever the voltage present at the non-inverting input exceeds that present at the inverting input. But in summing amplifier, the circuit produces output, so that is the sum of its two input voltage V1 and V2. So however, since the operational amplifier is connected in inverting mode, the output voltage is given by Vout equals to minus of V1 plus V2 because it is connected to the inverted input, right? So V1 and V2 are the input. So it adds two signals together and gives a combined output. See here we have given AC sine wave and this square wave, then you got this output, and here you have given two input, then you will get this one. So it compares which is bigger and it gives, but it adds both and you will get this one. So this is the summing amplifier. See, this is the formula. And next is the oscillators. So oscillators are the circuit that generate an output signal without the need for an input signal. So here we no need for the input signal. When the loop gain approaches unity, it results the unstable amplifier with infinite gain. So in that case, amplifier will oscillate. So since any disturbance will be amplified, and results in output. So positive feedback have undesirable effect, means Instead of reducing the overall gain, it reinforces any signal present and output continuously oscillate if the loop gain is 1 or greater. So, two main categories of electronic oscillators are, one is the sinusoidal oscillator, one more is the non-sinusoidal. So sinusoidal means it can produce an output having a sine waveform. So it is called sinusoidal or harmonic oscillators. So it can provide output at frequencies ranges from 20 Hz to 1 GHz. But non-sinusoidal oscillators means it produces output having a square or rectangular or sawtooth waveform. So that is also called as relaxation oscillator. So it can provide output at frequencies ranges from 0 Hz to 20 MHz. So that is about the two classification of oscillators. And negative feedback can be applied to an amplifier to form the basis of a stage which has precisely controlled gain. But if we apply positive feedback, it can be applied to an oscillator. So it will give the undesirable effect. And condition for oscillations, the feedback should be positive. Okay. So the signal fed back must arrive back in phase with the signal at the input. So this is the one condition. And second one is the overall loop voltage gain must be greater than 1. So here to create an oscillator we simply need an amplifier with sufficient gain to overcome the losses of the network that provide positive feedback. And next is the ladder network oscillator. The ladder network of, see here, this is resistor and this is the capacitor. Resistor R and capacitor C creates a phase shift needed for oscillation. The transistor amplifies the signal and feeds it back through the ladder. So this feedback causes the circuit to produce continuous sine wave output, that is V out. So it is a type of oscillator that uses a chain or ladder of RC parts to produce a steady oscillating signal. A simple phase shift oscillator based on 3 stages C, here you can see C and R. Ladder network. So TR1, here you can see the TR1, it operates as a conventional common emitter amplifier stage with R1 and R2 providing base bias potential and R3, this one R3 and C1. So it will providing the emitter stabilization. A number of circuits can be used to provide 180-degree phase shift. One of the simplest being a 3-stage CR ladder network. So here the total phase shift provided by CR ladder network is 180 degree at a frequency of oscillation. The transistor provides the other 180 degree phase shift in order to realize the overall phase shift of 360 degree or 0 degree. The frequency of oscillation of the circuit shown is given by, this is the formula to find frequency, F equals to 1 by 2 pi RC square root of 6. For oscillations to occur, beta should be greater than 1 by 29. Means the loss associated with the ladder network is 29. Thus the amplifier must provide a gain of at least 29 in order for the circuit to oscillate. And next is the Wein bridge oscillator. So see, this is the diagram. At one particular frequency, the phase shift produced by the network will be exactly 0. So if we connect the network to an amplifier producing 0-degree phase shift which has sufficient gain to overcome the losses of the Wien bridge oscillation will be result. The minimum amplifier gain required to sustain oscillation is given by gain equals to 1 by C1 divided by C2 and R2 divided by R1. So in Wien bridge oscillator, it has 4 resistors R1, R2 and R3 and R4 and capacitors C1 and C2 that is arranged in a bridge. So the name is Wien bridge. So this network creates a frequency selective feedback. Used with an amplifier, it produces stable sine wave at a specific frequency. So it helps generate a clean sine wave signal in oscillations. So this is about the Wien bridge oscillator. And frequency, to find frequency we have equation f naught equals to 1 by 2 pi square root of R1 R2 C1 C2. So we can write like this: when R1 equals to R2 that is equals to R, and when C1 equals to C2 that is equals to C, you can write the equation like this. So it happens most cases. So minimum amplifier gain will be 3. Particular frequency at which the value of resistance and capacitive reactance will become equal and produces maximum output voltage, that is this one. So and next is the single astable oscillator. So the capacitor C, here you can see it charges and discharges through resistor R. So while resistor R1 and R2 set a reference voltage at the non-inverting input, the op-amp continuously switches its output between high and low as the capacitor voltage crosses the reference, providing a continuous square wave at Vout. So a simple form of astable oscillator produces square wave output using just one operational amplifier, and this is the circuit. So it employs positive feedback with the output fed back into non-inverting terminal input via potential divider formed by this R1 and R2. So when power is on, the output Vout normally swings either plus VCC or to minus VCC. So assume C is initially uncharged, that time Vout equals to plus VCC. The upper threshold voltage means the maximum positive value at the inverting input will be given by this equation: VCC into R2 divided by R1 plus R2. The lower threshold voltage means the maximum negative value at the inverting input will be given by same equation, isn't it? Yeah, but here it is minus. Capacitor C charges through R and the voltage VC rise exponentially. So as voltage across the capacitor is greater than VUT, the output voltage will be rapidly fall to minus VCC. So capacitor C will then start to discharge through R, the voltage VC fall exponentially. So as voltage across the capacitor is slightly lesser than the VLT, the output voltage will rise rapidly to plus VCC. So this cycle will continue indefinitely. And next is the crystal controlled oscillator. Here you see the circuit. This is simple crystal oscillator test circuit. So an AC source divides the current through a quartz crystal which vibrates at its own natural resonant frequency. The crystal acts like very precise filter, allowing only its specific frequency to pass, making it ideal for highly stable, accurate frequency generation. To obtain very high level of oscillator stability, this crystal is generally used as a frequency determining device to produce high frequency stability in oscillators. So such oscillators are called as crystal oscillators. The quartz crystal vibrates whenever a potential difference is applied across its phases. So this phenomena is known as piezoelectric effect. The frequency of oscillation is determined by the crystal's cut and physical size. So these crystals are manufactured for operation in fundamental mode over a frequency range extending from 100 kHz to around 20 MHz. This is the symbol of crystal and this is the equivalent circuit RLC, and this is the CM. So the first one is in series resonant frequency Fs, which occurs when reactance of the inductance is equals to the reactance of capacitance, means XL equals to XC. Then F equals to 1 by 2 pi of L into C, square root of L into C. The second one is parallel to resonant frequency, means FP, parallel resonant frequency, this one. So which occurs when reactance of RLC branch is equals to the reactance of capacitor Cm. Sorry, this is Cm, okay. So that time Fp means parallel resonant frequency is equals to 1 by 2 pi square root of L into Ct. So Ct means this C into Cm divided by C plus Cm. So that's all about the crystal controlled oscillator. So this is about the operational amplifiers and oscillator circuit. For more classes, please watch the upcoming videos. Thank you all.